Pluto, once classified as an unmistakable and genuine planet in our planetary group, was viewed as an exceptional object for a long time. However, recent discussions led by popular astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited the debate about Pluto's status, prompting further examination of its role in the universe. These scientists have proposed that Pluto may actually be on a crash course with Neptune, sparking a flood of questions. How could such a massive event transpire? What might the impact mean for the two planets and the planetary group at large? Are we witnessing an extraordinary and unique cosmic event, or is there a more complex and profound explanation behind this hypothesis? We should dive into what a potential Pluto-Neptune impact could imply. Once thought to be a smaller, more distant object in the planetary group, Pluto still generates significant interest among scientists. According to key studies from leading experts, Pluto's orbit comes dangerously close to Neptune's, causing some astrophysicists, including Tyson and Kaku, to express concern about the possibility of a catastrophic impact between the two. The central question now is whether such an event poses a real threat to Earth. How could this happen in the first place? Pluto's orbit is one of the most unusual in our planetary system. It takes an extraordinary 248 years to complete one full revolution around the Sun, meaning that since its discovery in 1930, Pluto has not yet completed a single orbit. However, its path is not its only peculiar feature. It is also highly elongated compared to the more circular orbits of the larger planets. Furthermore, Pluto's orbit is tilted by 17 degrees relative to the plane of the planetary system, making it one of the most inclined orbits observed. This extreme tilt, combined with its elongated shape, adds complexity to Pluto's journey through space. A particularly fascinating aspect of Pluto's orbit is its interaction with Neptune's orbit. For about 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune, defying our expectations regarding planetary positioning. This raises an important question. Why haven't Pluto and Neptune collided yet? The answer lies in the gravitational forces at play within the solar system. Following Pluto's discovery, astronomers were perplexed by its orbit. Unlike other planets, which follow relatively flat and circular paths, Pluto's orbit is inclined and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's does not automatically result in a collision due to a gravitational interplay that stabilizes both paths. This balance, referred to as the three-body problem, illustrates how Pluto, Neptune, and the Sun interact through their gravitational forces. Like predicting future positions based on their current movements and the forces acting upon them, this phenomenon highlights how Pluto, Neptune, and the Sun's gravitational pull ensures the two objects never collide. Astrophysicists note that this stable interaction is maintained by a mechanism called libration, which ensures that when Pluto crosses Neptune's orbit, it does so at least 90 degrees away from Neptune. This prevents the two bodies from occupying the same point in their orbits at the same time. Additionally, Pluto's orbit exhibits degree libration, meaning it oscillates or shifts around its path, further reducing the risk of collision. Another significant factor in Pluto's orbital stability is the gravitational wobble effect, known as VZK wobbling. This describes how the gravitational pull from Pluto, Neptune, and the Sun influences one another, helping to maintain Pluto's orbit despite its seemingly erratic path. The three-body problem and these governing forces are crucial to understanding how planetary orbits evolve. These interactions not only shed light on Pluto but also enhance our knowledge of the broader workings of the solar system. Mathematical simulations conducted in the 1980s revealed that while stabilizing forces help keep Pluto's orbit secure, slight changes in its initial conditions could make its path more unpredictable over long periods. Despite such potential variations, Pluto's orbit has remained relatively consistent for centuries. Recent models have also highlighted how planets like Jupiter, Saturn, and Neptune help stabilize Pluto's trajectory. For instance, Neptune and Pluto follow a resonant orbit, meaning that for every 2 orbits Pluto completes, Neptune completes 3. This resonance is crucial for maintaining Pluto's orbital stability. However, Neptune is not the only planet influencing Pluto's path. Jupiter's gravitational effect also plays a significant role, and even Saturn has been shown to contribute to Pluto's orbital stability. These simulations suggest that Jupiter's gravity alone could maintain Pluto's orbit for billions of years, if not indefinitely. The cooperation of Neptune, Jupiter, and Saturn is, therefore, essential for ensuring Pluto remains on its current course. Without these stabilizing forces, our planetary system would be more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their orbits entirely. Studying such interactions helps us understand Pluto's orbit and provides valuable insights into the larger mechanics of the universe. Given this information, Pluto's orbit becomes even more intriguing when considering theories of a potential impact with Neptune. The study of Pluto's complex orbit demonstrates the dynamic nature of our solar system and how forces acting on one object can influence the entire system. It also reminds us that even seemingly chaotic orbits can still achieve a balanced state through these intricate interactions. The principle of orbital resonance plays a key role in this balance, explaining how Pluto's position and velocity, despite its irregular path, can still maintain stability over time. Programs simulating these orbital mechanics have provided valuable insights into how Pluto's orbit interacts with those of other celestial bodies, including Neptune. Small changes in model parameters indicate that even slight variations in Pluto's position or speed could significantly alter its trajectory. Despite stabilizing factors such as libration and resonance, Pluto's orbit can still be unpredictable. Minor variations in Pluto's initial conditions could lead to major changes in its long-term path. Nevertheless, despite its apparent unpredictability, Pluto's orbit has remained remarkably stable for billions of years, demonstrating an underlying order to its motion around the Sun, even when it appears chaotic. This unpredictability presents a challenge for astronomers, who must account for the evolving nature of planetary orbits. Although mathematical simulations are invaluable for predicting celestial behavior, they also reveal the limitations of our models. These simulations heavily rely on the accuracy of their initial conditions, and even the smallest error can drastically change the results, making precise predictions difficult. Pluto's eccentric orbit serves as a reminder of the ever-changing nature of the universe. While astronomers have made remarkable strides in understanding space, Pluto's erratic path underscores how much more remains to be discovered. The study of gravitational influences from giant planets like Jupiter, Saturn, and Neptune on Pluto allows scientists to gain valuable insights into the larger dynamics of the solar system. It reveals how the positions and movements of individual planets can have far-reaching implications for the stability of other objects within the system. Despite these stabilizing effects, leading astrophysicists have expressed concerns about a potential collision between Pluto and Neptune. Neil deGrasse Tyson, a prominent astrophysicist, offers a unique perspective on the mysteries of our solar system, using Pluto as an example. Tyson, who played a key role in reclassifying Pluto as a dwarf planet, emphasizes the importance of continuously evolving our understanding of celestial mechanics. Tyson argues that Pluto's reclassification was not a loss but a necessary change as our knowledge of the solar system grows. He views Pluto's strange orbit and its interactions with Neptune as evidence of space's inherent unpredictability. Although Pluto's orbit is stable for now, Tyson cautions that it could change significantly in the future. This possibility highlights how much is still unknown about the forces shaping the solar system and their broader implications. Tyson's perspective underscores the unpredictable nature of space, reminding us of the complexities of celestial mechanics. His analysis of Pluto's orbit in relation to Neptune emphasizes that even long-studied planetary movements can still hold surprises. Michio Kaku, another key figure in the debate about Pluto and Neptune, adds further insight into the potential risks and dynamics at play. His work expands on Tyson's by exploring how small shifts in gravitational forces could impact planetary stability over long periods. Kaku emphasizes that while Pluto's current orbit is stable due to resonance with Neptune, the solar system is not a static environment. External forces, such as passing stars, rogue planets, or even minute perturbations from the Kuiper belt, could introduce gradual instabilities. Over millions or billions of years, these seemingly minor changes could accumulate, potentially altering Pluto's trajectory in unexpected ways. One possibility Kaku discusses is the effect of chaotic motion in celestial mechanics. Even if a system appears stable in the short term, it can experience unpredictable variations over geological timescales. This means that while Pluto is not currently in danger of colliding with Neptune, there is always a degree of uncertainty when projecting planetary motions far into the future. Another key factor is the influence of the Kuiper belt, a vast region of icy bodies beyond Neptune. Pluto is one of the largest known objects in this region, but it is not alone. Kaku notes that gravitational interactions with other Kuiper belt objects could introduce slight changes to Pluto's orbit over time. These interactions, while small individually, might cumulatively push Pluto into a more unstable trajectory in the distant future. Additionally, Kaku and other astrophysicists consider the role of planetary migration. In the early solar system, planets like Jupiter and Saturn are believed to have moved from their original positions due to gravitational interactions with the surrounding disk of gas and debris. While major planetary migration has likely settled, minor shifts in the orbits of gas giants could still have cascading effects throughout the system. If Neptune's orbit were to change slightly, it could, in turn, affect Pluto's long-term stability. Despite these concerns, most simulations suggest that the resonance mechanism keeping Pluto and Neptune apart is robust enough to last for billions of years. However, Kaku stresses that our understanding of celestial mechanics is still evolving. Even with advanced computational models, small uncertainties in initial conditions can lead to vastly different predictions over long time frames. Both Tyson and Kaku agree that Pluto's case highlights the broader complexity of planetary dynamics. The interplay between gravitational forces, orbital resonances, and external perturbations creates a constantly shifting celestial landscape. Understanding these interactions not only helps us predict Pluto's future, but also enhances our knowledge of how planetary systems evolve over time. Ultimately, the study of Pluto and its relationship with Neptune serves as a reminder of the delicate balance that governs our solar system. While no immediate collision is expected, ongoing research into planetary interactions will continue to refine our understanding of the forces that shape the cosmos. As technology advances, new telescopes and space missions may provide even more precise data on Pluto's orbit and the wider Kuiper belt, helping to answer lingering questions about its long-term stability. Until then, the debate over Pluto's fate, whether it will remain on its current path or face disruptions in the distant future, remains an open question, inviting further exploration and discovery, the future of Pluto studies and space exploration. As debates about Pluto's orbit and its interactions with Neptune continue, advancements in space exploration and astronomical research will play a crucial role in uncovering new insights. With the advent of more powerful telescopes and space probes, scientists are poised to refine their understanding of Pluto's motion and its potential long-term fate. Upcoming space missions and observations. One of the most significant contributions to our knowledge of Pluto came from NASA's New Horizons mission, which provided unprecedented close-up images and data on the dwarf planet in 2015. The mission revealed Pluto's diverse surface, complex atmospheric interactions, and evidence of geological activity, challenging previous assumptions that Pluto was simply an inert, icy body. Building on these discoveries, scientists are now advocating for a follow-up Pluto orbiter mission that could further investigate its internal composition, atmospheric changes, and orbital peculiarities. Such a mission could also provide critical data on Pluto's gravitational interactions with nearby Kuiper belt objects, which may subtly influence its trajectory over time. Beyond Pluto, future space missions are likely to target the Kuiper belt as a whole, helping astronomers determine how gravitational forces in this region contribute to the overall dynamics of the solar system. Studying Pluto's interactions with its neighboring objects could provide valuable insights into the long-term stability of its orbit. The role of exoplanetary studies. While Pluto remains a key subject of study, its peculiar orbit has also inspired broader investigations into exoplanetary systems. Many exoplanets discovered in other star systems exhibit highly eccentric or tilted orbits, similar to Pluto's. This has led scientists to compare the gravitational interactions seen in our solar system with those shaping distant planetary systems. For instance, studies of exoplanets in multi-star systems have revealed how gravitational resonances, similar to the ones between Pluto and Neptune, can prevent collisions and stabilize planetary orbits over long periods. By studying Pluto's behavior in our own solar system, scientists can refine models that predict the movements of exoplanets in complex celestial arrangements. Long-term cosmic implications. While current models suggest that Pluto will remain in a stable orbit for billions of years, the nature of the universe itself is constantly evolving. Over extreme timescales, the dynamics of the solar system could change due to factors such as galactic interactions. As our solar system orbits the Milky Way, it passes through different regions of interstellar space. A close encounter with a passing star, though highly unlikely, could disturb the orbits of outer solar system bodies like Pluto. Dark matter and unknown forces. Some physicists speculate that dark matter, which makes up a significant portion of the universe's mass, could have subtle but long-term gravitational effects on planetary orbits. While these forces are not yet fully understood, ongoing research aims to determine whether they play a role in shaping celestial mechanics. Sun's evolution. In about 5 billion years, the Sun will expand into a red giant, altering the gravitational balance of the solar system. While inner planets like Earth will likely be consumed, the outer solar system, including Pluto, may experience shifts in its orbital parameters due to changes in the Sun's mass distribution. Conclusion: Pluto as a symbol of cosmic exploration. Despite its classification as a dwarf planet, Pluto remains a subject of immense scientific interest. Its highly eccentric orbit, interactions with Neptune, and position in the Kuiper belt make it a fascinating case study in celestial mechanics. Whether Pluto's path remains stable indefinitely or shifts due to unforeseen gravitational influences, its story is a testament